So, deep learning, it turns out, is a subset of the more general field of machine learning, and machine learning is a subset of an even broader field known as artificial intelligence that's been around for many, many years, and to be honest is mainly science fiction rather than science fact. What distinguishes deep learning specifically from the slightly broader field of machine learning is that deep learning uses neural networks to spot hidden patterns in data sets. The word deep in deep learning refers to deep neural networks, and deep neural networks are usually taken to mean neural networks with more than one hidden layer. So deep learning and neural networks are a very, very hot topic these days that's really emerged over the last 10 years or so. But deep learning is just one part of a broader field of machine learning. Aside from neural networks, there are quite a cluster of what you might call classical machine learning algorithms that are still in use today and still very applicable. So classical machine learning algorithms include algorithms for performing tasks like classification and regression and clustering and anomaly detection, with algorithms such as support vector machines or decision trees or random forests. Neural networks are just one of many machine learning algorithms then. And neural networks have really come to the fore because they're very good at spotting patterns in very, very large data sets. However, for many problems, these classical machine learning algorithms are perfectly adequate. So don't assume that just because neural networks and deep learning are a very hot topic these days, that a deep learning algorithm or a neural network is necessarily what you want to solve your particular problem. There are many problems for which so-called classical machine learning algorithms are totally appropriate, particularly appropriate for smaller data sets. So these algorithms could be all you need. However, if you're trying to deal with a more complicated problem, maybe a computer vision problem, and you've got a very large data set, then a neural network could be for you. So deep learning, getting a deep neural network to learn something about patterns within a data set, is one example of supervised learning. With a supervised learning, we start off with a training data set that consists of both inputs and outputs, and our model or neural network is trying to learn how to predict the outputs from the inputs. So we train up our model or neural network using a training data set, and then deploy the model somehow in the field where it's used to try to predict the outputs given novel inputs. So supervised learning, which includes deep learning with neural networks, is clearly divided up into two phases, a training phase and an inference phase. In the training phase, we train the model using a data set, typically a very, very large data set, where the model attempts to learn how to predict outputs from inputs. We then deploy the model in a field and go into a second phase, the so-called inference phase, where we present our model with novel inputs that it's never seen before and it attempts to predict the outputs. These days, training is typically done on big GPUs. Neural networks can be trained using CPUs or GPUs, but GPUs have performance advantages for training. So it's pretty much standard practice these days to train neural networks using a big GPU or maybe several GPUs. When it comes to inference, however, there are many, many more options, and it turns out that GPUs are not necessarily a great platform to use for neural network inference. So inference can be performed across a whole range of computing devices, from low-end MCUs through to high-end application processors, DSPs, specialized neural network accelerators, or, the topic of today's webinar, FPGAs. So the topic of the webinar is deep learning for FPGAs. And you can see here that FPGAs come into deep learning typically in the context of inference rather than training. So even if you are going to deploy a neural network model on an FPGA in the field, you may still train up that network on GPUs. That's not to say that FPGAs absolutely cannot be used for the training process, but the training process for a neural network, or indeed any machine learning model is just a computational problem of executing an algorithm, and GPUs are pretty well suited to that task. So let's talk about neural networks in particular and training neural networks. So for training, for any kind of supervised learning process, we need labelled data. And the archetypal example of a labelled data set will be a set of images where each image carries with it a text label. So in this case, we've got images of cats, and our labels consist of breeds of cat. So that will be a typical training data set that we're going to use to train up a neural network. What we're then going to do is to take the labels, which otherwise known as the ground truth, taken to be the truth, the correct labels for each of the training data samples, and we're going to use a so-called cost function to compare the ground truth with the predictions from our model, in this case a neural network. So we'll feed our training data set into the neural network. The neural network will come up with a bunch of predictions, and those predictions will initially be very, very bad predictions. And we'll use our cost function to compare the predictions of the network with the ground truth. And because the predictions are going to be very bad, the cost is initially going to be very high. A neural network itself typically consists of multiple layers. Certainly for a task such as image recognition, we're going to have a so-called feed-forward network where we feed the images in at the inputs of the network. The images are then propagated through the network layer by layer until they reach the outputs, which form a prediction, and the prediction is fed into the cost function. So neural networks consist of multiple layers. Each of those layers consists of individual units or neurons. And you can see immediately that an architecture like this may be a pretty good fit with an FPGA. So you can quite naturally imagine how an architecture like this might fit into an FPGA, where each of these individual units or neurons would be low-level FPGA cells maybe, and we can organise those cells into this sort of two-dimensional structure. So already we can see an FPGA could be a good implementation vehicle for a neural network. The individual neurons, or artificial neurons, each have a bunch of inputs and a bunch of outputs, and they perform a calculation in two parts. First of all, each neuron performs a linear function, which is simply a weighted sum of the inputs from the previous layer. So we're taking the values from the previous layer, which would be, in a general case, floating point numbers. We're multiplying each of those numbers by a weight, adding all those values together in a linear function. And then we compute a non-linear function known as an activation function. So the basic computation within the units of a neural network are a linear function, a weighted sum, followed by a non-linear function. When it comes to the non-linear function, there are many choices in common use these days. The ReLU function is one of the most popular functions today, but there are others. You also see logistic or sigmoid functions, these S-shaped curves, and variations on ReLUs you'll see as well. So a deep neural network then is a neural network with multiple layers, more than one hidden layer. We feed in data samples at the inputs of the network. Those data samples propagate through layer after layer of hidden unit. Each hidden unit is performing a weighted sum followed by some sort of non-linear activation function. And then the data converges to the output of the neural network, where the network makes predictions that are fed into the cost function. So this whole computation, again, is a pretty good fit with FPGA architectures. So the basic computations that are being performed here are similar to the computations that we'd need for DSP that FPGAs are pretty good at. Also, the nonlinear activation functions maybe could be implemented pretty naturally using lookup tables in FPGAs. So all in all, you could imagine that an FPGA might be a good implementation target for an architecture like this. There's a number of different kinds of neural network that are making it out into the wild. Deep learning and neural networks are still a very, very active research topic, but certain kinds of neural network are really being used quite seriously in practice now. So generally, the sorts of networks we're using are ANNs, or artificial neural networks. Then there are a few particular flavours of neural network you're sure to hear about if you haven't done already. The CNN, or convolutional neural network, is particularly good for image processing. Then comes the regional CNN, which is good for object detection. So object detection refers to figuring out whereabouts objects are within an image. And then the so-called RNN, or recurrent neural network, that's a neural network with loops in. Recurrent neural networks are used in natural language processing, whether it's speech processing or text processing. So deep learning and neural networks overall is still a hot research topic, but it's also really very, very practical and being applied seriously in the real world. And certain applications like object recognition and object detection and natural language processing are effectively leading the way.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of John's webinar, Deep Learning with FPGAs, whenever you want by heading over to our website www.doulos.com/OD and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.